Physicist Michio Kaku once said that time and space are like a fabric, something that can be bent, stretched, and maybe even folded. This opens the door to the possibility of time travel, at least in theory. In a recent interview, Kaku made a bold statement: time, as we know it, might not actually exist. Even before this, our understanding of time was already puzzling. Concepts like time speeding up or slowing down, relativity, and time dilation all added to the confusion, leaving scientists constantly questioning the nature of time itself. But now, the line between theoretical physics and observable reality is beginning to blur. New findings are pushing us to rethink everything we know about space and time. The James Webb Space Telescope has delivered concrete evidence supporting these groundbreaking ideas. According to Einstein's general theory of relativity, space and time form a four-dimensional, flexible structure known as spacetime. This fabric is warped by mass and energy. Stars, planets, and black holes bend it, and that bending is what we perceive as gravity. The theory of relativity reveals that time slows down under stronger gravitational forces or at higher speeds. For instance, an astronaut near a black hole would experience time more slowly than someone farther away. This phenomenon has been confirmed through experiments using highly accurate atomic clocks on satellites and aircraft. These findings suggest that space travel may come with unforeseen consequences. Astronauts who depart in one era might return to Earth in an entirely different one, as more time would have passed on Earth than for them aboard a spacecraft, even if their journey only lasted a few years. While long-distance space travel remains a dream for the future, time dilation isn't just a cosmic curiosity, it's something that occurs right here on Earth, reminding us that time is relative and might even be manipulated. But what about the universe itself? Does it use time? Rather than picturing the universe as a rigid stage where stars and planets perform, imagine it as a flexible fabric woven from space and time. This is exactly what Albert Einstein proposed in his general theory of relativity, one of the most groundbreaking ideas in modern science. According to Einstein, space and time aren't separate, fixed backdrops. Instead, they form a single, dynamic four-dimensional fabric. In this fabric, all masses and forces influence one another. A massive object like a planet, star, or black hole bends this fabric, just as a heavy ball placed on a stretched sheet causes it to curve. In this way, mass shapes the flow of space and time, and everything within the universe responds to that curvature. Unlike objects pushed or pulled by invisible forces, most things move by following the natural curves in the fabric of space, what we call gravity. This isn't just a metaphor. Einstein's theory of general relativity was dramatically proven during a solar eclipse in 1990, when astronomers observed light from distant stars bending around the sun's mass, exactly as predicted by the curvature of spacetime. Gravity doesn't just influence motion, it also affects time itself. For example, a clock placed on a mountain ticks slightly faster than one at sea level because the spacetime curvature is weaker at higher altitudes. While this difference is negligible in daily life, it's critical for systems like GPS, satellites, and space probes. Without adjusting for these time distortions, they would deliver wildly inaccurate data. Seeing spacetime as a flexible medium leads to some mind-bending possibilities. If space and time can truly bend and stretch, might we one day manipulate them? Theoretically, yes. Space could be compressed, stretched, or even folded, much like paper. That idea sparks fascinating questions. Could we create shortcuts through the universe? Could we travel through time? This is where the concept of wormholes comes in, hypothetical tunnels through spacetime that might connect two distant regions of the universe as if they were side by side. Instead of journeying for years or millennia, what if you could simply step through a cosmic door? This idea is more than science fiction. Back in 1935, Albert Einstein and Nathan Rosen proposed a theoretical model, now known as the Einstein-Rosen bridge, describing a tunnel linking 2 points in spacetime. It would act like a hidden passage through the universe, a shortcut within the folds of space itself. Remarkably, this concept doesn't violate known physical laws. But can it actually be built? In theory, yes. In practice, not yet. Wormholes, if they exist, would be incredibly unstable and would require exotic conditions to remain open. Still, the possibilities remain one of the most intriguing frontiers in physics. While Einstein and Rosen originally described wormholes as natural structures, some theories suggest that these tunnels through spacetime could also be created artificially. Things get even more intriguing when we consider not just connecting distant places, but different points in time. Certain models propose that if one end of a wormhole were accelerated or placed in a powerful gravitational field, it could develop a time difference relative to the other end. In theory, this would make time travel through a wormhole possible, both into the past and the future. As of now, there's no direct evidence that wormholes exist, but there's also no proof that they can't. Many physicists, including Michio Kaku, believe they could be real, not today perhaps, but one day. It's even possible that the universe already contains hidden wormholes. Some unusual phenomena observed in deep space or in cosmic voids might hint at natural spacetime distortions or wormholes. To achieve such a feat, we'd need more than just ordinary matter. Stars, planets, gas, and dust all obey gravity, curving spacetime inward. But to keep a wormhole stable and open, we'd require something entirely different: exotic matter with negative energy, a substance that pushes spacetime outward, acting against gravity. In other words, a kind of anti-gravity. This exotic material could be the key to bending time itself. This concept already exists in theoretical physics and is known as exotic matter and negative energy. Unlike ordinary energy, which always has a positive energy density, negative energy refers to a state where there is less than nothing, something that quantum physics suggests is possible. One well-known example is the Casimir effect. When two conductive plates are placed extremely close together in a vacuum, quantum vacuum fluctuations cause a measurable pressure. The energy between the plates is lower than the surrounding space, creating a region of negative energy density. This phenomenon has been demonstrated in laboratory conditions, although only on a very small, nanometer scale. If this effect could be scaled up, it could theoretically generate warp bubbles or even stable wormholes. However, producing the vast amounts of negative energy required for such structures is far beyond our current technological capabilities, and no such phenomena have yet been observed in the universe. Still, the theory holds up, and scientists are actively exploring how these concepts might one day be realized. Physicists like Kip Thorne, who advised on the film Interstellar, and Michio Kaku speculate that advanced civilizations could already be using such technologies, or that similar phenomena may have naturally occurred in the early universe. Another intriguing area of study is dark energy, which also appears to have a repulsive effect on spacetime. Although it's not the same as negative energy, it demonstrates that the universe contains forces that oppose gravity, an essential property for enabling wormholes or warp drives. For now, exotic matter remains hypothetical, but research continues to push the boundaries of what's possible. It may sound like science fiction, but the concept exists within the boundaries of physics. At the Particle Accelerator in Geneva, scientists are working tirelessly to uncover exotic and negative forms of energy, and even find practical ways to harness them. Rumors persist that artificial wormholes have already been created there. Online discussions even speculate whether these experiments might be tearing holes in spacetime, causing distortions we can't detect, because they may have already become part of our reality. Time travel, a concept that pushes the limits of what's physically possible. Whether in movies, novels, or scientific debates, the idea of journeying into the past or glimpsing the far future holds undeniable allure. But what does modern physics have to say about it? Surprisingly, the answer is often yes. According to Einstein's theory of relativity, under specific conditions, time can indeed be manipulated. Time dilation is the first step. If one end of a wormhole is accelerated or exposed to an intense gravitational field, it creates a time offset between the two ends. A person traveling through such a wormhole could potentially emerge in their own past. As mind-bending as it sounds, the math supports the possibility. But with time travel comes a host of paradoxes. The most famous is the grandfather paradox. What happens if you go back in time and prevent your own grandfather from ever meeting your grandmother? The consequences challenge our very understanding of causality.